Okay, now if you just let's look at page 29, okay. The part A is the one that I really want to go through. All right, now for part A1 here, it was mentioned to you that a gravitational field can be represented by lines of gravitational field. Okay, now when you hear mention of things like lines of gravitational force, like the ones that you're seeing in the question here, is actually referring to your field lines. Okay, gravitational field may be represented by field lines, like what I mentioned in the first part of your lesson for this chapter. So state what is meant by a line of gravitational force. State what is meant by a field line. Okay, what does a field line actually tell you? In other words, so if let's say I have a mass here and then I have some masses, like the mass has a gravitational field around it like this, and it's directed inwards, like so. If I were to place a test mass right over here in the field, what will happen is that that mass will be pulled towards the larger mass at the center here. There's a gravitational force that is acting on the test mass that's pulling the test mass towards the larger mass here. Okay, so at the beginning of this chapter, I mentioned to you before that field lines can be used to represent your gravitational field, but the field lines themselves have a direction to them. And the convention is that if you want to determine the direction of the field, normally it will follow the direction of the force acting on a test mass that is placed inside the field right now. So in our case, because our test mass is this one, and the gravitational force acting on it is this one, is directed inwards. So our field lines must be directed inwards in terms of their direction. So here, when we ask you what is meant by the field line here, what does your field line actually tell you? You can actually say a number of things. You can actually say, number one, it indicates the direction of force on a small test mass, or it will also be correct to say that it indicates the path in which a small test mass will move, because the force is directed inwards, so obviously the object will move inwards. Now, in some variation of the same question, sometimes the force may be replaced with another different term called acceleration. Okay, it indicates the direction of acceleration on a small test mass, which is actually kind of true, because this Fg is your resultant force. The resultant force in turn causes an acceleration. So if you learn in dynamics AS, we mentioned to you before that resultant force produces an acceleration, and that the acceleration must always be in the same direction as your resultant force. So it's actually correct to say so also. It tells you the direction of the force, it tells you the direction of the acceleration of a test mass inside the field, or also the path in which the test mass will move. Okay, so this is what a field line actually means. Now, if you look at part 2, part 2 is saying that by reference to the lines of gravitational force near the surface of the Earth, explain why gravitational field strength G close to the Earth's surface is approximately constant. Okay, so when it comes to your questions of gravitational field, sometimes you may be asked to explain why certain things are constant. If you look at page 30, which you did in the last lesson last week, page 30 was talking about suggest why for small changes in height near the Earth's surface, gravitational potential is constant. So that time we went through the process of looking at the equation where we say that because the small change in height is very much smaller than the radius of the Earth itself, your R plus H is actually equal to R itself. So actually, if you compare between 2 points near the Earth's surface, the potential will just be constant. Okay, so that was what we did in the previous lesson. Now here, if you look at page 29, they're kind of asking you the same thing, but it's for a different quantity. They are not asking for you for gravitational field strength. The one previously in page 30 is asking for your gravitational potential. So just to recap, gravitational potential was negative Gm over R. When it comes to gravitational field strength, it is actually Gm over R squared. Okay, that's the difference between these two in terms of the equation. The only difference is that there's a square term for field strength. So here they're asking you something similar. Why is it that near the surface of the Earth, the field strength is going to be approximately constant? Now, if you had tried to explain this in the form of an equation like you did in page 30, that one actually would be okay also. But here, the question actually mentioned to you by reference to the lines of gravitational force. So this one, you cannot use equation to explain. If I try to explain to you in the form of an equation right now, it will be the same as gravitational potential, where I basically tell you, if I have a point here, where this one is radius r, and then for a small change in height or close to the Earth's surface, let's just say this point, this one is h. If I'm interested in 2 points over here, point A, maybe I should use a blue color here just to see it better. If I'm interested in 2 different points, point A and point B, I can say that gravitational field strength at A is actually going to be Gm over R squared. Whereas gravitational field strength at B will be Gm R plus H squared. Okay, so the thing now is that H would be very much smaller than R. Therefore, R plus H is actually the same as R itself. So this one would in turn mean that GB is actually going to be the same as GM over R squared. So when you compare between these two, they are actually going to be the same. So we can say that they're going to be constant. This is if you want to explain it in the form of an equation. But here, the question has really specifically told you to explain using your lines of gravitational force. They want you to explain in terms of your field lines. Why can we say that for very small height near the surface, we can actually assume that gravitational field strength is constant? Okay, so it actually kind of makes use of what we learned in the first part of the lesson. I mentioned to you that field lines is a measure of field strength. Okay, I mentioned to you that field lines is a measure of field strength. I mentioned then further that the closer the lines, the stronger the field. Okay, that is the main thing here to refer to when it comes to answering this question. So let's just say, for example, I have the surface, this is the planet that I'm talking about. And then the gravitational field lines around it would be something like this. This is an exaggerated diagram. Like this. Okay, so this is how you would expect your field lines to look like for a planet like Earth. Okay, for example, the lines itself would be radial by nature, because one of the other things I also mentioned to you before this was that field lines are always perpendicular to contacting surface, or contact surface now, if you would. Okay, they're always perpendicular to your contact surface. So my field lines must always be perpendicular to my contact surface. My planet itself, Earth, is assumed to be a perfect sphere. So the cross-sectional area would be a circle. So when you try to draw the field lines, it must maintain 90 degrees with the surface. So the end result is that it will appear to be radial, like what you're seeing here. Okay, so one of the things that you will be able to see is that if I were to go further away from the center of the mass, let's just say I go in this direction here, maybe I draw it in red. We'll go away from the center of the mass in this particular direction. What you're interested to see is how the line spacing actually changes. You can see that in terms of the line spacing, the spacing increases, okay? By right, the spacing increase, therefore, G should decrease. But here, the question is really just asking you one particular thing. Near the surface of the Earth, meaning to say you're really considering only a small change in height above the surface. Let's just say, for example, you are really considering just this small h when compared to the large radius of the Earth. So that small h will be something like this. It's talking about this little area here. I mean, this little section here, which I highlight in orange right over here. Okay, so you're really just talking about this particular section here. Now, if you're trying to zoom in on this particular section, the thing is that when you zoom in that close with respect to how the entire field actually looks like, which is like this, the thing that you will notice is that when you try to zoom in at such a small distance, your field line, this, as I said, that this is the surface of the Earth, zoom out, zoom in, your field lines probably look like this, okay? So for this small distance of h, right over here, the thing that people can say is that the line spacing appears to be almost the same, okay? This one, for our case here, we can actually say that the line spacing, the line, the spacing is approximately same. Therefore, G is constant. Okay, for this small section of H, small height of H that you're considering, you will notice that the change in the line spacing is more or less negligible. The line spacing is actually approximately the same. Therefore, G is constant. That's what you're trying to explain here in your particular question. So your answer would probably be worded like this. First answer would be using that the lines of force or field lines are radial for a sphere like Earth, because in the first place, they must always be perpendicular to your contacting surface. This is where your first mark comes from. Then after that, you can actually just say, the second sentence, I think I need to go and modify it because it seems to be a bit too long. Closer to the surface, the height of the surface is small compared to the large radius of the Earth. What I could say is, now that I read it close, the height near the surface is small. The height above surface is small. Yeah, actually, you don't need to write this statement. Closer to the surface. You can actually just say that the height above surface is small. The height above surface is small compared to the large radius of the Earth. Thus, the lines are approximately parallel. The part where you say that the lines are approximately parallel is where your second mark comes from, okay? But in the first place, you kind of need to explain why do you say that they're almost parallel in the first place? Why do you say that the line spacing is approximately the same? It's because the height is very small compared to the radius of the Earth itself. That's why I can say that they are approximately parallel. That's why I can say that this one is approximately parallel. Just like that, okay? Then after that, you end with saying that parallel lines actually indicate constant gravitational field strength, okay? For some reason, they would just say that all parallel lines, and for your marking scheme, whenever they say parallel lines, they always assume that the line spacing are equal. Okay, parallel lines here, they say the line spacing are equal because for some people, they maybe if they go and think a bit further, they may argue that if I have something like this one versus this one, these four lines are also considered to be equal. These four lines are also considered to be parallel. But then when I look at the line spacing, this line spacing versus this line spacing are not the same. So I cannot really say that the field strength is constant here, right? But here, for the purpose of your exam in the marking scheme, it seems to be that whenever they say that the lines are parallel, they by right assume that the spacing is equal. Okay, in case you're wondering. Okay, right. Hi Kai Chen. We are on the page 29 of the gravitational field and circular motion worksheet. Okay, we actually discussed out part 1A. We're actually discussing question 1A1 and A2. Okay, I've just finished discussing A2. All right. Okay, so to recap, these are the 3 points. No? Lines of force are radial for a sphere like Earth. Height above surface is small compared to the radius of the Earth, which in turn means that the lines are approximately parallel. Just these 3 points. Sorry, not these 3 points. These 2 points plus the last point, parallel lines indicate constant gravitational field strength. This will be the 3 points that you need to write. Okay, so that one should be okay. All right. Okay, so let me just clear off everything from here. All right, part B is actually referring to part B is actually referring to your escape speed. I think I did some similar question on escape speed with you last week, Alicia. So it's kind of like the same thing, but this one I'll just go through really quickly, right, to make the question complete. Now, they tell you the moon may be considered to be a uniform sphere of diameter 3.4 times 10 power 3 kilometer and a mass of 7.4 times 10 power 22 kg. And the moon itself has no atmosphere, meaning to say it will not have any kind of air resistance. During a collision of the moon with a meteorite, a rock is thrown vertically up from the surface of the moon with a speed of 2.8 km per second. Assuming that the moon is isolated in space, determine whether the rock will travel out into distant space or return to the moon's surface. Okay, will that rock actually be able to escape all the way into infinity? So you can kind of visualize that this is the moon. You have a meteorite that somehow hits the surface of the moon, like so. And then after that, it causes a rock to be sent flying off with a speed of 2.8 km per second. So in the last lesson, it was mentioned to you before that for any objects to fly away into outer space without going back into the planet itself, you actually need to have a certain minimum speed called escape speed. Okay, so here what you really just want to do is to find out the escape speed and then compare it with the actual speed here. All right, so this one you probably could just use the equation for escape speed where VE is square root 2gm over r. Because here the question never really asked me to say explain your working, the derivation is probably not required, but although it's 4 marks now, okay? They gave you C1. C1 would probably be for the fact that they want to see that you know this equation. Square VE is square root 2gm. And then after that, the few subsequent marks will be for you subbing in your values. G is 6.67 times 10 power minus 11. Your big M is the mass of your moon. Your R is actually the diameter, the radius of your moon. But here you're given a diameter value. You need to divide by 2 to get the radius R. Okay, this is the radius. So you're given the value of diameter. Make sure you divide the diameter by 2 to get the radius. And then after that, this 10 power 3 here is you changing kilometer to meter. Okay, so just get all the values in eventually you get the answer as 2.41 times 10 power 3 meter per second, but change it to kilometer. Meter change to kilometer divide by 1,000. So eventually you will get 2.41 kilometer per second. This is your escape speed, the minimum speed to escape all the way into infinity. All right, but you compare it with your actual speed right now. This is your actual speed, 2.8. This is the minimum speed to escape. This is the required speed. Okay, minimum required is this, but actual right now is 2.8. So the conclusion that you will be able to draw from this is that since your actual speed is 2.8 km per second, which is more than your escape velocity, the rock will therefore escape into distance space. Okay, so that is for this. Okay, so this is one. Then I go to another question. This is actually the more difficult ones. Then after that, I'll move on to your new chapter, which is thermal properties. Thermal properties is relatively easy. Let me just find out the question. Where on earth is it? It should be somewhere around here. Okay, wait on, just let me find out the question. It's either 11, page 11. Yeah, page 11. Okay. Okay, so just have a look at page 11. June 16 P41. Yeah, just have a look at June 16 P41. Then let's go through this. Okay, now by reference to the definition of gravitational potential, explain why gravitational potential is a negative quantity. Okay, by reference to the definition of gravitational potential itself, explain why gravitational potential is a negative quantity. So gravitational potential, it was mentioned to you before that phi is equals to negative gm over r. Explain why it will always be having a negative value. Okay, this one actually I've actually discussed in detail last week in one of the questions. Okay, so this particular question I've actually discussed it in detail last week. That question at that time was worth 3 marks. Okay, the one that I discussed last week, which is actually talking about the same thing. So for this one, I won't dive so deep into it. Okay, if you want to know the detailed explanation, you can actually refer back to the lesson from last week. Okay, so the main things that you just probably need to write is this: gravitational potential at infinity is defined as 0. This is where the first mark comes from. Then after that, gravitational force is attractive. So work is done by object as the object moves from infinity. Then after that, at that time, when I discussed this, I mentioned to you that GPE decreases from 0, therefore gravitational potential will be negative. Okay, so in that question last week, in the same question last week, for another year, when it was worth 3 marks, gravitational potential at infinity is defined as 0. This is one. Gravitational force is attractive. This is another one. And then work is done by object as it moves from infinity. This is your other mark. Okay, so you could have actually used the answer for a 3-mark question, for a 2-mark question. You still be getting the full thing, the full marks. Okay, so this is one common question that will come out. All right, just make sure you know there are always these 3 points. As long as you get the 3 points, you write it out, it will fit all kinds of variation of explaining why potential is a negative quantity. All right, okay, now the one that I really want to talk about is actually part B. Oh yeah, another thing I should probably mention to you here is this. I have a tendency to use work is done by object, which is actually correct. If you look at the marking scheme, they don't use the term work done by object. Instead, they will use a very weird term called work got out as the object moves from infinity. What does it mean by work got out? That means that there's also work getting in, if there's getting out. So I'm not too sure what this is the term that the marking scheme tends to use, but to avoid any confusion, you can actually just use work done by or work done on. This is actually a better term to use. Okay, just so you know. Now look at part B. Two stars A and B have their surfaces separated by a distance of 1.4 times 10 power 12 meter, as illustrated in this figure. Point P lies on the line joining the centers of the two stars. This point P is on a line joining the center of these two stars. Stars A, star B, this is their centers. There's a line between them, and point P is just right on the line itself. Okay, so the distance x or point P from the surface of star X may be varied. Is actually this point P here is actually measured from star A. Okay, this one is how they measure the x value. Okay, they say that the distance of point P from star X can actually be varied. And then here, the variation with distance x of the gravitational potential phi at point P is as shown. Okay, your graph here is a graph of potential versus distance x from star A. Okay, now how do they get this graph here? This one in gravitational field, we don't really explain much why it is how you get it, but in electric field, in the chapter later after this, you actually need to understand how they got this graph. So I'll just explain it here first for you. Let me just erase all certain things. Yeah, let me just explain to you first how they got this. Now, if I tell you you have star A, this is star A, and then this is star B, and then there's this little line joining the centers of the two stars, like this, and I have a particular point P in between those two stars. Now, star A has its own gravitational field. Likewise, star B would also have its own gravitational field. Okay, but because you see star A and star B are situated relatively close to each other, their fields, you can actually say that the fields for star A would actually overlap with the field for star B. Okay, because they are relatively close lah. Okay, 10 power 12 meter is actually not a small distance by normal human standard, but relatively speaking, for when you're talking about gravitational field, this is quite close. So when it is at this distance, the two fields, the two gravitational fields for star A and B, it is reasonable to assume that they will actually overlap. You need to say, you see, the field line for star A will extend all the way here. The field line for star B will extend all the way here. So the thing is that there will be a region where the field lines for star A and star B overlap, which is right over here. Okay, so when they overlap, because field lines, or rather gravitational field, is a vector, when they combine, you will get some sort of resultant. Okay, so in the line, along the line between the centers of these two stars, what you will be having is a gravitational field that is the resultant of star A and star B. Okay, so the take-off point here is for you just to recognize that if you're talking about the region in between star A and star B, whatever gravitational field that you have here is actually the resultant of the gravitational field of star A and star B added together, because the field lines are overlapping here. Okay, so right now you have a point P that is of interest to you. Now, if I want to find out the resultant quantity here, let's just say right now I am interested in finding out the resulting gravitational potential at this point. I know that the resulting gravitational potential at this point must be due to A and B combined together. Okay. When you're talking about the gravitational potential at P, this one is actually the resultant potential due to A and B. Okay, so how are you going to find the resultant potential due to A and B? Now, in any kind of fields, gravitational field, electric field, and magnetic field, you will usually need to have something to test a point inside the field. In our case, when we want to test a point inside a gravitational field, we will actually need to use a test mass to test a point inside the field. So if I want to find out something about point P right now, I will actually put a test mass here in order to find out certain things about that point inside the field. So right now, if I put a test mass here, you consider this. If I just consider this pair of masses, star A and test mass, I can say that there will be a potential due to A, which is GMA over RA. Okay, this one is I consider the potential that is caused by A itself. So if I find the potential caused by A itself, it will be phi A equals to negative GMA over RA, where in our case, RA is this one, the center to center distance between the star and the test mass. Okay, so this one is if I consider this pair. Now I could also repeat the analysis for a different pair, namely between star B and the test mass itself. So in my case, I can also say that the potential due to B would be, for example, negative GMB over RB, where RB right now is actually this one. Okay, so far so good. So just understand that at this point P, I put a test mass. I want to find out the potential, resulting potential, but I have to consider the potentials individually due to the different masses. So I first consider the potentials due to mass star A, and then I also consider the potentials due to star B. Okay, now when I want to then find out the resulting potential at P, which is the resulting potential due to A and B itself, what I can say is this: potential at P is actually potential due to A plus with potential due to B. So I'm going to get negative GMA over RA plus with negative GMB over RB. Okay. So from here, what I can then say, in order to make things short, remember your X is this one measured from star A. So when X changes, phi A and phi B, when X changes, when X changes, RA and RB changes. Therefore, phi A and phi B changes too. So from here, you will get the conclusion phi P varies with x. Okay, because these two will change with distance, giving you a change in your potential at P. So overall, your graph shape would look like this. All right, if you sub in the values. Okay, I'm not going to discuss why the shape looks like this yet. This one will be something that we will discuss in detail in another different chapter, electric field. But for now, I just need you to know this concept. When you're talking about between two different masses right now, a point between the two different masses, whatever you have in between is actually the resultant field between of the two masses. So you need to know a bit of how to find out the resultant field. Okay. Now, so this one is okay. This one is talking about, for your case, scalar quantities now. All right, for potential. Now, what if I want to find out, for example, the gravitational force at point P? If I want to find an expression for the gravitational force at point P. Okay, it's a similar analysis, but this time you need to be careful a bit because gravitational force is a vector. So how would the analysis kind of differ? So I give you again that same two different masses like this, and I still have the distance, sorry. I still have the distance between the two masses, the line between the two masses like this, and then I have a point P which I'm interested. So I'm interested to find out what is the gravitational force acting for a mass placed at point P. So again, because I'm talking about trying to test a point inside the field, I will actually try to put a test mass right over here. Let's call this test mass M again. Right? Let's call this your test mass M. Okay. So same thing as before. Whatever you have in between the two masses is the resultant of the two masses itself. Okay. So if you want to find the resultant, you actually kind of need to analyze individually the effects due to the masses individually, like what I did for potential here. Just like I told you that when I want to find the resultant in P here, I want to find out the effects due to A, and then I want to find out the effects due to B before I add them up. You are trying to do the similar thing here for gravitational force. You want to find out the resultant gravitational force at point P, but before you can do that, you must consider the effects due to mass A and mass B separately. So what I mean by that is that if I want to find out the gravitational force at P, I know that it's the resultant of gravitational force of A and B. So let's just consider the effects of gravitational force due to A itself. Now, if I'm talking about these two masses, star A and the test mass, the gravitational force due to A alone on the test mass would be in this direction. This one is Fg for A, okay? Because the test mass will be attracted towards star A, right? If you just consider these two, okay? The gravitational force due to A will be towards the left. But if I repeat the analysis for a different pair of masses, which is this one, the gravitational force on the test mass due to B will instead be in the opposite direction. Meaning to say, it will be right over here. Okay, it will be in the opposite direction, FGB. Okay, so now what I'm interested is to find out the resultant gravitational force at point P. Let's call this force FP. Okay, this one would be the resultant due to FGA and FGB. So because FG is a vector, direction is important. Okay, gravitational force is a vector, so there is a direction to consider. When I want to add up the gravitational force, this is what I expect to see. Fp is going to be, let's just say that going to, yeah, let's just say I add them out. This one will be FGA plus with negative FGB. Okay. So why is there a negative here in the first place? It's because you see FGA is towards the left, FGB is towards the right. When I add them out, because one of them is acting in the opposite direction, one of them will be a negative. In my case, I assign B to be negative. All right. So this is how you're going to get the resulting gravitational force at point P. Okay. Now another thing I should probably mention is this, because your gravitational force is, actually make I write the answer. Okay, I'll just write it here. Gravitational force is Gmm over r squared. So this one will actually be Gma m over ra squared plus, sorry, not plus, minus GMB over, times m over rb squared. Okay, so eventually you see that in a similar reasoning, when x change, RA and RB change, so your FGA and FGB will also change. So your FP will also change with distance. Okay, so that's just one thing I need you to see. Now, you just bear this in mind first. There's one part of this that I'll need to explain again later on. So just understand that whatever point that I'm talking about in between these two masses, it is talking about the resultants of the two masses. Okay, the effects of those two masses combined together. All right, you will need this to do part 2 later. All right, okay, now let's just start with the question. If you look at the next page, you have a rock of mass 180 kg. Wait, let me just erase this. You have a rock of mass 180 kg that moves along the line joining the centers of the two stars from star A towards star B. Now, use data from the figure to calculate the change in kinetic energy of the rock when it moves from point where x is 0.1 times 10 power 12 meter to the point where x is equals to 1.2 times 10 power 12 meter. State whether the change itself is an increase or decrease. Okay. Now, if you look at your graph, when you are talking about x being 0.1 times 10 power 12, this is actually from the surface of star A. And then when you move to 1.2 times 10 power 12 meter, this is actually going towards the surface of star B. You're actually moving from star A to star B right over here. Now, they're asking you, if I were to move from star A to star B, what would actually be the change in kinetic energy of the rock? If you recall the diagram looks like this. I'm just going to draw it here. You can actually refer back to the diagram in your notes. I mean, you can actually refer to the diagram in your worksheet if you want to. The diagram actually looks something like this in the first place. Okay, it actually looks something like this. Okay, so this one was where you have the 0.1. This one was where you had the 1.2 in terms of the distance, not x now. Okay, so right now they're telling you that you are basically moving from this point to this point. You're moving in this direction, like this. Okay, from star A to star B. So they want you to find out, if I move like that from star A to star B, what is my change in kinetic energy? That is my change in kinetic energy. But the graph that you have, if you notice, is actually not KE versus distance. It's actually potential versus distance. Now, there's a relation between potential and GPE that I mentioned in one or two lessons before this. If you recall that I mentioned to you before that potential is GPE over M, or that time I wrote in the notes U over M, you can actually say that GPE is M times phi. GPE at a point is equals to the mass times the potential at the point. From here, the change in GPE is actually the mass times the change in potential. Okay. Now, if you are able to find the change in GPE, you will be able to find out the change in kinetic energy because of conservation of energy. All right. So let me just erase this. From the graph that you have right now, right over here, you can actually find the change in potential because this is a graph of potential versus distance. From A to B, you can find the change in potential, which from there, you can then find out the change in GPE, which is mass times change in potential. Okay, you can find out the change in GPE by taking the mass times the change in potential. Now, by conservation of energy, change in GPE is actually the change in your kinetic energy, because conservation of energy will tell you that if you are gaining energy in one form, you will lose energy in another form, or you lose energy in one form, you will gain energy in another different form. Okay, so right now you can see that you can find out the change in GPE from the graph, but the thing now is your GPE a decrease or an increase? You can see from here that you're going from here to here. You're actually decreasing. Yeah, your graph is negative, but you will still be considered as decreasing in value. Let's just say, for example, this is negative 10, and then I decrease to negative 16. This is still considered decrease. So here, your potential decreases. You could say that your gravitational potential energy is also decreasing. Okay, so here, if I know that changes in GPE is equal to the changes in KE, if I already established that my GPE is dropping, my KE therefore must be increasing. Okay, so this is the understanding right over here that you can see. If you want to find the change in kinetic energy, you find out first what is the change in GPE, because the GPE is the change in GPE is the change in kinetic energy. That's why I can write this. Change in KE is the change in GPE, which is in turn the mass times change in potential. So mass times the change in potential, just take the difference between the two. You don't really need to bother about the negative. You want to include the negative is fine, but you really just want the difference in the magnitude. You can actually just omit out the negative, take higher value minus the lower value, which is 14 minus 10. Don't forget the power of 10, multiply with your mass, you're going to get the change in K as this 7.2 times 10 power 10 joules. All right. But how do I then know that the KE will be increasing or decreasing? Is because I know that GPE decrease, therefore KE increase. So I can say that KE increases by this value. Okay. So that's for this part. So I think this one no issue. The part 2 is the one that has a bit of an issue. Okay, because this is the one that people have problems understanding. Okay, so if you're okay with that, then I'll just move on to part 2. All right. This is where it gets a bit complicated. All right, now, for part 2, if you read the question, at a point where x is 0.1 times 10 power 12, the speed of the rock is v. Okay, meaning to say at this point here, you are actually projecting a rock with a speed of v. okay, where you at the from the surface of star A. Find out the minimum speed v such that the rod will reach the point where x is 1.2 times 10 power 12. What is the minimum speed required in order for your rod to be able to reach this distance, which is actually star B itself? So they're telling you what is this value of V that you need to give your rod so that it can actually reach star B. All right. Now, you may be tempted to do something like this where you say, oh, I go and find out because the previous question here, you actually already said, oh, change in GPE is equals to change in KE. So I already found out the change in GPE before this. It was 7.2 times 10 power of 10. So my change in KE now probably will be half mv squared. And then after that, we go and sub in the value of the masses, which is 180, to find out the value of V. Now you do something like this, it is not correct. Okay, you will not be able to get the answer because this is something that you probably have been doing in your AS physics. You say something, change in this energy is equals to change in that energy, and then after that you want to find the speed, you just sub in all the relevant variables to find the V, right? Now, in your current case, for this part 2, you cannot do this, okay? This one is not the correct way of doing this. You actually need to consider something else, okay? You need to consider something else. You will still be using change in K equals to change in GP, but you are not going to be using this one. You're not going to be using the values that you found in part 8. Now, why do I say that? This one I need to erase off a lot of stuff. Just bear with me a little. Okay, let me just erase off the entire thing on the right hand side. This is not required. I will need to refer back to the diagram on the left that I actually drew for you. Okay, because I stopped halfway, right? So now you look at the diagram on the left that I just drew earlier, where I explained to you how you go and find the resultant gravitational force for a mass that's placed inside the for a mass that's placed between the two stars. So I told you that it is actually Fp equals to Fga plus Fgb. Okay, so this is what I mentioned to you. Now, if you look closer at the diagram, that I just drew, because you notice that the resultant Fg, which is Fp here, is actually Fga minus Fgb, you could actually come to a conclusion that somewhere in between the two stars, you would have Fp equals to 0. Because you see, when your X changes, Fga will change, Fgb will change, but they are having one minus the other. So it will come to a point when you move along this line, Fga will be equals to Fgb, such that they completely cancel off. In that case, you will actually have Fp being 0. Okay, let's just say for the sake of our discussion, we say that right over here is where your Fp or your Fnet is 0 lah. Okay, this thing here, Fp is kind of like your Fnet. Okay, let's just say that at this point that I just indicated to you, this is where your Fnet is 0. All right, so what I'm interested is what happens to the side on either side where your Fnet is 0. If let's say I'm talking about the left hand side, what is the direction of your Fnet? If I'm talking about the right hand side, What is the direction of your fnet? So let's try and see what happens. Now, if I go towards the left-hand side, I would actually be able to say that FGA is actually more than FGB. Therefore, fnet is going to be towards the left. Okay. Now, how do I know this? I can actually see it from the equation. You see, if you're talking about your RA and RB here, you can actually say that RA is this little thing here. And then RB is this thing right over here. Okay, RB. So, say for example, when you go more towards the left, your RA would drop, so your FGA would increase. But your RB would increase so that your FGB would drop. So you see, in your case here, if you go towards the left, because FGA is increasing while FGB is decreasing, you will eventually come to the conclusion that FGA is more than FGB. That's why here I can say this at the top. FGA is more than FGB, so my resultant net force is actually going to be towards the left, because FGA in the first place was towards the left, FGB was towards the right. So FGA is getting larger, the force towards the left is getting larger, obviously my net force will be towards the left. Okay. At the same time, my force towards the right was getting smaller. All right. So this is what I can say about the left-hand side of my diagram. What about if I go towards the right-hand side of my diagram? What if I'm talking about this part here? The converse will be true. If I go towards the right-hand part, what you see now is that in this case, FGB will be more than FGA. Therefore, fnet will be towards the right. Okay, it's a similar reasoning like what I did below here, where I can say that if I go towards the right, let me just draw it here. If I go towards the right, RA drops so that FGA increase, whereas RB, oh, sorry, RA increase, my mistake, sorry. RA would increase so that FGA would drop, but then RB would drop so that FGB increase. So your conclusion is FGB will become more than FGA. Okay, so this is what you're actually getting. All right, this is but you looking at it in the form of an equation now. But for some people, their common sense will be something like this. If my test mass moves towards A, the effects due to A will be larger than B. So obviously, my overall effect will be due to A itself, which is towards the left. But if I move towards the right, I'm moving more towards B, the effects due to B will become stronger. So the overall effect will be due to B itself. This is how some people make sense of it, which is kind of true, but you can actually see it from the equation itself. All right, whichever works your way, right? You just see which one works for you to remember. Okay, so the thing here is that you just need to know that at along a line between the two masses right over here, there will be one point where fnet is 0, and then on the left hand side, fnet will be towards the left. On the right hand side, fnet will be towards the right. Okay, so that one is the one thing I just want you to see here, so that I can actually explain part 2 for you of your question. Now, let's just say, for example, I draw for you this line where I tell you fnet is 0, And then this part here is where F net is going towards the left. And then this part here is where F net is going towards the right. Now, let's just say, for example, I project to you a mass with a certain velocity. Now, remember last time I mentioned to you in kinematics, in one of the recorded lessons, if you have watched it, if my motion is towards the right, but then I have a resultant force towards the left, which is basically opposite to your motion, your object will actually slow down, isn't it? So if let's just say right now, I'm talking about the situation between the two stars right now. When I first project my mass from star A, let's just say that this is where star A is. And then I want to make sure that it reaches star B. The thing that will actually happen here is that between this section here, your mass will actually slow down because your resultant force is opposite to your motion. But after you've gone past this F net equals to 0, you actually start to speed up because your net force is now towards the right. Okay, so in a similar manner, if I tell you V is this side, but then your F net is now same direction as your motion, you will actually speed up. Okay, so this is actually what is happening to your mass as you project it from star A to star B. It will actually slow down in the first part, and then after that, it will speed up at the other part. But the thing now is this. What do you suppose would happen if I don't project my object with sufficient speed, with a certain minimum speed? What will happen is that, let's just say, for example, I project it at 10 meters per second. I know that the object will slow down to 0. But what if I slow down to 0 right over here, 0 meters per second? My object move until this point is slowed down to 0. So what do you suppose will happen? If my object slows down to 0 here, it will actually be pulled backwards. It will actually be pulled back. So in my case, this one is not insufficient minimum speed. This one I would say that it is insufficient minimum speed. Okay, I did not project it fast enough, so it slows down to 0 even before reaching F net equals to 0. So at that point, my F net is towards the left. My object will just be pulled back downwards, pulled back towards star A. It will never be able to reach star A. It will never be able to reach star B. Okay. Now, what if then I tell you, okay, this time you learn your lesson, you go and project your mass with an even higher speed. Maybe you project it with 50 meters per second square. Right? Such that at this point, F net equals to 0, you've gone past, I mean, if you project it with sufficient speed, let's say 50 meters per second, it will slow down, but it slows down when it reaches the F net equals to 0, you still have some speed. Let's just say maybe now you are still left with 5 meters per second. So let's just say you project a higher speed at 50 meters per second, it slows down, and it happens to reach the point where F net equals to 0 with a certain speed, F net 5 meters per second. What do you suppose will happen then? Because you've reached F net equals to 0 with a certain speed, what happens after that is that you already have a net force acting along the same direction as your motion right now. So what will then happen is that your object will now speed up towards star B. Maybe now it will speed up at 20 meters per second. I mean, it speeds up and then it will hit star B. Okay, so this one, I can say that this one, once it reaches this point, this one will be pulled to B, star B. Okay, because what then kicks in is that your net force is in the same direction as your motion. You don't need to do anything already. It will no longer slow down. It will instead now start to speed up towards star B. Okay, so what you really want to do now is to find out that instant where you're just able to reach star B. You want to find the speed that's just sufficient for you to reach star B. Meaning, say you project it with a certain speed v, and then you assume that it reaches this f net equals to 0 at 0 meter per second, because this is kind of like the limiting case, the point at which you're about to be pulled towards star B. You would consider this case in your calculation. Okay, you would want to consider this case. So here, what you really want to do is this. This is the, if I try to write it out for you, this is the limiting case one at the point of being pulled to star B. Okay, so the thing that you just really need to realize from here is that if I go from here to here, then I would have a change in KE. All right, now that change in KE will be the same as my change in GPE. Okay, that change in KE will be the same as my change in GPE. So if I go from here to here, I would have a change in KE. That change in KE will be the equivalent of my change in GPE between these 2 points. So I want to find out what is the change in GPE here, so that I can find out what is the change in KE, which will allow me to find out this V. Okay, I'm not too sure whether I'm making sense for you here. Maybe it's better if I just draw the diagram. I will need to refer back to the other diagram, the original graph. This was your graph of potential versus X, and then this is your graph here like this, right? I tell you that this one is star A, this one is star B. Now, where do you suppose is where your F net is equals to 0 from the graph? The point where your F net is equals to 0 is actually right over here. This is the point where your F net is equals to 0. Okay, so this is actually the point where you're kind of assuming that I project my object with speed v, and then it reaches here at 0 meter per second. So I can actually work out between these 2 points, the change in KE is equals to the change in GPE. What you really want to do is that you want to find out the change in GPE so that you can then equate the change in KE, which in my case, the change in GPE is m delta phi from here to here. Okay, that's what you're trying to do. All right, your workings that you see on the screen is actually trying to do that for you. You notice that the change in GPA that I'm trying to find, I will say change in GPA. The change in GPA I'm trying to find is actually between these 2 points. Okay, it is between 10 and 4.4. Okay, so this is 4.4, this is 10. This change in potential multiplied with the mass will give me my change in GPE, which in turn will be my changes in KE. Okay, so my KE here, change in KE, is actually half mv squared minus 0, giving me this value. Okay, then you solve and find out your speed. It is half times 180 v squared equals to 1.008 times 10 power 11. square root it, you're going to get the answer 3.35 times 10 power 4 meter per second. Okay, can? Yeah. How do we know for sure that the position of that graph as f net equals to 0? How do I know this thing here is going to be f net equals to 0? Okay, this one is actually quite simple. I mean, it's very easy to see. Put it this way lah. You see, if I draw it for you here, let's just say this little point here, you can see from here that from this point to this point, GPE is increasing, my KE is dropping, right? Then after that, right after that point here, my GPE starts to drop, my KE starts to increase, right? So I know this point is the point where F net is 0, because like just now I mentioned to you, when your F net is 0, on the left hand side, F net is towards the left, your object will slow down. But on the right hand side of F net equals to 0, your net force is towards the right, your object will speed up. So one way you can see that is by looking at your KE change. You will notice that at this point here is where your KE starts to have a different change. Before this, it was dropping. Suddenly now it's increasing. So I know for sure this one will be the point where F net is 0 in the first place. Okay. It's not just a convenient point we can pick. I mean, we can actually reason that one will actually be the point where F net is 0. Okay, right. So that's for this one. Yeah, this question is actually pretty difficult. All right. The explanation of it is difficult, but then you see the working is actually pretty straightforward. All right. For all your gravitational field questions, this is about the only question that requires you to think of things in this way. You actually encounter this kind of things again in electric field. It's in another separate chapter.